Welcome everyone. This is our course project for operating systems and cloud computing, where we have worked on distributed computing using Apache Hadoop and Spark. Firstly, distributed computing is the use of multiple interconnected computers to solve a computational problem. Apache Hadoop is a distributed computing framework for processing and storing large datasets across clusters for commodity hardware. It uses HDFS for distributed file storage and MapReduce for distributed data processing. Hadoop is also fault tolerant. It knows hardware failures can and will happen and adjusts accordingly. Apache Spark is a distributed computing framework that provides in-memory data processing and processing of batch, streaming, and machine learning workloads. It can be used with various data sources such as HDFS, HBase, Cassandra, and Amazon S3 and supports multiple programming languages including Java, Scala, and Python. Spark processes data in real time such as streaming feeds from Facebook and Twitter. Apache has an interactive mode allowing the users more control during the job run. Apache Spark is very much popular for its speed. It runs 100 times faster in memory and 10 times faster on disk than Hadoop MapReduce since it processes data in memory RAM. Now, I'd like to briefly explain the procedure of installing Hadoop on your device. First, download the tar file from the link here and extract the Hadoop folder from the tar file onto your device. Also, if Java isn't installed on your device, be sure to install JDKKit on your device as well. Second, update .bashrc. Export the Java and Hadoop path into .bashrc of the device. Third, modify Hadoop environment files. Export Java path into Hadoop env.sh, mapred.env.sh, yarn env.sh. Fourth, configure .xml files. Change configurations of HDFS site XML, mapred site XML, core site XML, and yarn site XML. Fifth, format the name node. Formatting name node is necessary to create a new file system and should only be run while setting up a new cluster. The code for the same is Hadoop name node -format. If this is done later, data stored like metadata and blocks will be lost. Sixth, and the last step will be start all. Start -all.sh. This should get all the daemons on the master node. For now, the cluster is on a single device only, due to which only one device acts as both master and slave node.
Setting up a multi-node cluster. So initially we need to generate the RSA keys in all the slaves and master computer and add them into the authorized keys file section so that master can access to the slave computers. Configure the .xml files as they are already configured in single node setup. So master IP should be replaced instead of localhost in HDFS site, core site, yarn site, and mapred site .xml. These configurations give access to the master to start Hadoop in slaves. Format the name node and start the cluster with startall.sh command. Spark installation. Download and extract Spark tar file from the official Apache Spark website. So after extraction, update the bashrc with exporting the Spark path. Modify the Spark environment files. So in the Spark env.sh file, we have to add the master IP, Java path, Hadoop path, yarn path, and Spark local IP accordingly. Modify the Spark default configuration file. We have to add the Spark web URL, master port number, and could also set the amount of memory to use, number of cores to run, and number of instances as per requirement. Then in the master node, add the slave's IP address in the workers file and start the cluster with startall.sh. RSA keys are shared among the cluster members. Cluster members can connect to each other with SSH. Let me show you the connection to each slave through SSH. SSH master to connect to master node, SSH slave 1 to connect to slave 1, and similarly to slave 2. To start the Hadoop cluster, go to Hadoop directory, start Hadoop from sbin as sbin startall.sh, then Hadoop daemons get to start. In the master node, there should be 5 daemons running in Java process state as JPS. And 2 daemons running in slave node as data node and name node manager. We can see this in slave 1 and slave 2. This shows that our PCs are connected in Hadoop cluster. To start the Spark cluster, go to Spark directory. Start the Spark from sbin as sbin startall.sh. This will start the worker and master daemons in master node at Java process state and just worker in slave node. This shows our PCs are connected in Spark cluster. Hadoop Web UI can be accessed with master IP at 9870 port number. In Hadoop Web UI, we can see the number of live nodes alive and Hadoop URL for the cluster. And in the data node section, we can see the information about slave nodes and the data and memory distribution among the slaves. And in the utilities section, we can browse the HDFS directory. Spark Web UI can be accessed with master IP at 8080 port number. In the Spark Web UI, we can see the number of nodes alive and the amount of memory cores allocated to the Spark job. These Web UI can only be viewed when Hadoop or Spark is running in background and can only be viewed within the cluster members.
Once the cluster is set up, we proceed to uploading a dataset to the HDFS cluster by following these 3 steps. First, we select a dataset from either external websites or from inbuilt Spark example datasets. For this project, we have done the latter. We then create a directory in Hadoop Utilities directory using the command hadoop fs-mkdir/data. This created directory data can be viewed in the utilities directory of our HDFS cluster. Before going to the final step, we shall look at our dataset, which is in the format of LIBSVM, where each line represents a data point. The first column is the target variable or class label, which is either 0 or 1 in this case. This is the result class that is being predicted by this classification algorithm. The remaining columns represent the features or predictors which are encoded in a sparse format using the index:value notation. Now we'll upload this txt file containing our dataset into the data directory we previously created using the command shown here, thereby uploading the file to our HDFS cluster. Once this dataset is present in the HDFS cluster, we can run algorithms on Spark cluster using this dataset. The algorithm we have chosen to run for this project is the Logistic Regression with Elastic Net algorithm, which is a powerful technique for binary classification problems, particularly when dealing with high-dimensional datasets with many features. It is widely used in machine learning applications such as image classification, text analysis, and biological data analysis.
This code is a Java example of running logistic regression with ElasticNet on a labeled dataset in the LIBSVM format using Apache Spark's machine learning library. We start by initializing a Spark session, following which we load the training data which we previously uploaded into the HDFS directory using the spark.read method. After loading the data, the code creates an instance of logistic regression and also an instance for logistic regression for multinomial family. And then a model is fitted to the training data using the fit method. We now compile the algorithm, which is in a .java format, into a .class format in the terminal with the help of jar imports provided by Spark. We bind the .class file into the jar file using this command, which we will submit to the Spark cluster using this command. Now we can go to Spark's job browser, on which we can see the executors and the driver and the event timeline. Also, in the web UI of Spark, we can observe that the running applications has been incremented to 1 from 0. Upon completion of the algorithm, we obtain the output in the terminal, which displays us the values of coefficients, intercept, multinomial coefficients, and the multinomial intercepts. Now when we go back to the Spark web UI, we can observe that the time taken for this entire process to be completed on 3-node cluster was 1.2 minutes. Contrary to this, when we ran this algorithm on a single node cluster, it took us 2.3 minutes. Thereby, we can conclude that usage of distributed computing framework like Apache Spark is ideal for big data handling and associated algorithms. We would now like to extend a heartfelt thanks to our esteemed faculty member Dr. Animesh Chaturvedi for guiding us throughout this course and giving us an opportunity to learn market-relevant technologies. And now we shall introduce ourselves.
This is Janvi.
I am Tarun.
I am Prerna.
And I am Virinchi. Thank you.